Okay. Let's see if we get some luck finding these eigenvectors. So for lambda equals 1 plus 2y, this is first one is minus 2v1I plus 2v2 equals 0. Minus 2v1 minus 2v2I equals 0. Okay, so let's see if these are equivalent. So and then so 4 and 5 and okay 6 and 7. Okay. So if I multiply 7 by I think we get the same equation, right? Minus 2 is 1I plus 2. Yeah. Um, which is, let's write this down, 2v2 minus 2v1 equals 0. And this is actually 0 plus I sigma. If we consider some, let's say, non-zero v1, actually this is, yeah. Is that all? I think there might be something else. So, because if that's the case, then every eigenvector for a complex eigenvalue would be 0. That I don't think that's true. V2 is 1. So the spell is this spell is. Okay, so I think we have a choice for V1 and V2. So if we consider some non-zero real part, for example, V2 in this case is 1, then we can consider V1 to be I, right? Yeah, so I think the eigenvector for this case would be I and 1. I think it's non-zero, so that's good. Uh, we can check if AV equals lambda V. Let's see that A is 1, 2 minus 2, 1. Is I 1 and lambda was 1 plus 2. Let's see if both the sides match or not. So RHS is simply Mhm. Okay, so there's a difference in sign, I think. Let me check that this is clear. Yes, that's always true. So it would depend on what you choose to be V2. If V2 is also, let's say, A plus IB, then you'll have to substitute in this equation, sorry, this one, and then find out what E1 should be. That's always. But you also saw that in the case of real numbers, right? Real eigenvectors or eigenvalues. So it's something like k times this. So in that case, we had one eigenvalue, but there could be multiple eigenvectors. That's it. So we usually choose k to be a simple one, maybe one or something that scales down these vector elements. That's the matrix exponential. So just to recall, if x is just a scalar number, e to the power x is simply 1 plus x and so on. Yes, yes, yeah. About the origin, so you can see this. So if it's a matrix, we let's say if it's A, some n by n matrix, then e to the power A, and let's say t is some scalar. So because we are using t because we know that if x dot equals ax, x is also a scalar, a is also a scalar, then the solution of the differential equation is simply e to the power infinity times x. So we want an analog of this for the matrix equation or the state space one, right? Ax. So if we are considering an LTI system, this is the formula AT plus A square by 2 factorial T square. So you can actually have K well here there. So it's K factorial and so on. Gives the solution to the state space equation. Sorry. Solution of x dot equals A of x. Sorry, AX. So that is, let's say the initial condition is some x naught. And we're considering time from 0 to, let's say, some capital T, which is finite. So the solution of x dot equals ax would be x at any given time t is e to the power t times x naught. And since this matrix lets you go from 0 to time t, so this is also known as a state transition matrix phi. Phi at any given time t, starting from some initial time. Right now we are considering this to be 0. State transition matrix. Yeah. Yeah. It is. I mean, in what sense do you mean? I mean, this is computable for if you have A well defined. So if A is for an LTR system, you can actually find a, we will see this, you can find an analytical expression for this. You can just keep on adding this and you'll find out that all the elements have some closed form expressions. Let's see. See, so we've done this, right? Phi of t is, or e to the power of t is the Laplace inverse of Si minus A inverse. Let's begin with the question. Yeah. Were you saying something? 0, 1, minus 2, minus 3. And then the question is to compute the free response. So let's say that there is some initial condition x10 and x20. Now we want to compute the Laplace inverse of Si minus A. So this is simple. In this case, it's S plus 3 minus 1 and 2 square plus 3s plus 2 psi minus A inverse in this cases. Change the elements of the main diagonal and these are of opposite signs. Okay. You can factorize the denominator. This is I think s plus 1, s plus 2 and s plus 3, 1 minus 2 and s. So the Laplace inverse is simply by the partial fraction expansion, right? So we need the Laplace inverse of s plus 3 over s plus 1, s plus 2 or just s. Sorry, this is, and then 1 over s plus 1, s plus 2. All the other elements are combinations of this one. Okay, so let's do this quickly. 1 over s plus 1, s plus 2. So C1 is 1 over s plus 2 at s equals minus 1. This is minus 1, so this is going to be e to the power minus t minus e to the power minus 2t. And then we have another expression. So it's s over s plus 1, s plus 2. This is c1 over s plus 1 plus s plus 2. Laplace inverses plus 2 e to the power minus 2t. So all the others are combinations of these two expressions. So I'm going to write down the Laplace inverse of this matrix. This is e to the power minus t, it's minus 2t. So this is another entry. And then this one is minus t plus 2 e to the power minus 2t. Okay. So this is also e to the power 80, which is also pi t comma 0. So x at any time t is simply this matrix times the initial condition. Got another question. What is 0 minus 2, 0, 1, 0, 1, 0, 3? And x at time 0 is given to be 0, 1, 0. Okay, so we have to find out what e to the power 80 is and what is the solution at any given time. So again, you can just write this down, si minus a, sorry, s minus 1, s minus 3. And you can repeat the procedure from the previous question, right? So I'm not going to do the partial fraction expansion, but I'll write down the final expression for e to the power 80. This is 2 e to the power t minus e to the power 2t 0 e to the power t 0. So there's a difference between the matrix exponential of this question and the previous one. So you can observe that the exponential powers are positive, and in the previous one these were negative, right? So in the previous case, for any initial condition, if you multiply by this, the solution would go to 0 as t tends to infinity, right? Because all the exponentials have negative powers. So it would be something like 1 over e to the power t times some constant, let's say x10. This is a constant or independent of time. So as t becomes infinite, the solution would converge to 0. But let's look at this case. So we have e to the power 80 and the initial condition is also given. So what is x of t? This is 0, e to the power t and 0, right? We extract this column. What does this mean? This means that the solution would become unbounded after some time, right? It would just keep on increasing. So you can either check stability from the eigenvalues, or sometimes it's also evident when you can actually compute the state transition matrix. Yeah. Yes. Yeah, you can. So if you have, it is. Yeah. It would be growing with time. Yes, you can do that. So instead of actually solving all of this, you can just put a differential equation, solve using RK4, plot it, and you will actually see that the solution becomes. Yeah, yeah, you can. Yeah, you can. That's also a good option. So this is when you can actually compute, but that's not always the case. If even if you have a simple system which you're working on, you cannot really find the state transition matrix. Uh, yeah, yeah. So if it's even if you have like a 4 by 4 matrix, it becomes difficult. Yeah, it's really not good. Yeah, you can. Yeah, yes, yes, you can. So that's only for bounded and bounded. No, it's not always. So if you have to comment on stability, it's always if you talk about the Lyapunov function, that's always a standard way to go. Yeah. Because if you have asymptotic stability from the Lyapunov function, then Vivo stability is always uh, guaranteed anyways. But the converse is not true. Now let's look at the solution of external equals. Mm, sorry, I mean there are like many steps, right? You either use Lyapunov function or you diagonalize and comment on the eigenvalues, or you use this state transition matrix. Yeah. Is that what you mean? Yeah. Okay. Mm, okay. Yes, you can. Yeah, yeah. I think if you have the eigenvalues, you have that similarity transformation P, right? Okay, so let's say that you have diagonalized the system and that matrix is A bar. Okay, so and you want to figure out what e to the power 80 is. A is the original A matrix. So if A is P, sorry, A bar is P inverse AP, then A is P A bar P inverse, right? Okay, so if you want to calculate this, there's a very nice proof of this. So you have P A by P inverse. And what's special about this? That you can always find e to the power A bar T if A bar is diagonal, right? So let me just show that one second. So I had, yeah, yeah, yeah. Yes, exactly. They are decoupled, right? Exactly. Yeah, yeah, yeah. So if it's like, what you can, yes, you can. So that would be a B vector for every eigenvalue. Those would be decoupled equations, and you can actually find the converse. Hmm, I'm not sure. Because usually what I work on is that if you already have AX plus BU, don't generally diagonalize, we just work with this original system. But you can do that. If you want to focus on modes of the system or the frequencies, you can actually diagonalize and work on that. That's also fine. Yeah, 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 yeah. Yeah, because actually you have transformed the system. I think that's what you're saying, right? Because now the new variables don't make sense physically. Because, yeah, yeah, yeah. Okay. So now let's talk about relation of x dot equals ax plus b, given some initial condition x0. Alright. Okay, so in this case, x of t is e to the power at times x naught. That's the autonomous part. And due to the input, this is t0 to sometime t, e to the power a t minus tau. So tau is the variable of integration, b and u tau. Indeed. So we are considering LTI systems. So A and B matrices are independent of time. Correct. And in the language of state transition matrix, this is simply phi t minus t naught. So in this case, it's t minus tau b u tau t tau. Okay. So this is in the time domain. And if we have Laplace, if we can compute Laplace inverse, then this is Laplace inverse Si minus A inverse applied to x naught plus this integral becomes Laplace inverse of phi of s b u of s. Alright, so let's look at a question. x1 dot x2 dot equals 0, 1, minus 2, minus 3, x1, x2 plus 0, 1 times u. So let's consider a step input in this case, u t u of t. Okay, so e to the power at is simply this. You already know at this point how to calculate this. So I'm just going to write this down directly. This is 2 e to the power minus t minus six. Alright. And now we have to compute that integral from 0 to t e to the power a t minus tau b u tau. So this simply is 1. And we need to compute the integral of, let's say, what's b is 0, 1, right? just the integral of, let's say, minus t minus tau. So you can actually integrate element wise and you'll get something like this. Let me just read this. This is half e to the power minus t at minus a. So this is, okay. So if this is the case, then what is x of t? It is, let's say, x at time 0 is the vector 0, 0. So x of t is simply this, right? Because e to the power at x0 is, sorry, I just put this up. So in this case, we just have the force response. Because we have assumed that the initial condition of the system is at the origin. Alright, let's see if we have, so let's come to the next section. This is properties of the state transition matrix. Alright, so let's recall them. So if we are considering t to be 0, then the state transition matrix is identity, right? Because it relates x at any time t and the initial condition. So if we are considering t equals 0, this means that this is identity of the appropriate size. So if we have n states, this is going to be n by n. Okay, so this means that phi at any time 0 is always identity. Now the next one. So we already know that x of t is, let's say, phi t x0. So if this is the solution to the state space system, then if we substitute this, we should be able to satisfy the differential equation, right? The differential equation is x dot equals ax. This is d by dt phi t x0. And at the other side, this is a phi t x at 0. So x of 0 is independent of time. This is simply d by dt of phi t x0 equals a phi t x0. So this gives us a very important property of the state transition matrix, that its derivative is simply a times phi. Alright, now let's not talk about this. So, alright, so if we solve the system, let's say x dot equals ax, what we have is a trajectory of states in time, right? We start somewhere at x equals 0. At time t1, let's say we are at t1 and then x at t2. So if let's say that if we have a solution for this part, can we also have a solution for this as well without using the initial conditions, right? So if we are just considering this, so this means that the initial condition is actually x of t1. Okay. So in that case, let's see what happens. So x at t2 equals phi at t2 times x at t1. But x at t1 is simply phi of t1 x at 0. Yes. Yeah. That means. Mm, yes, for LTI systems. So for initial conditions, you can actually reach anywhere in the solution of the state system. I wrote this down correctly. Yeah. So this means that we can actually compose these state transition matrices. So in other words, it's like x at t2 is some, let's say, okay, I think I wrote this down. Okay. Let me just rewrite this. So x at t2, if we start from x0, that's a state transition matrix. And if we start from t1, this is phi of t2 minus t1, x at t1. So the actual relation between the state transition matrices that phi of t2 minus 0. So in case if t0 is not 0, that's a relation is actually equals to phi of t2 minus t1, phi t1 minus t1. So there's another property of the state transition matrix that if you go back in time, it's simply the inverse of the state transition, right? So phi at minus t is phi inverse at t. And the last one is phi t is a non-singular matrix. Yeah. Mm. Non-singular is that it's invertible, right? That's what the term is. So it's like just right. Sorry, it is invertible. That's another term for invertibility that was, it's non-singular. Yeah, okay. Mm, yeah, in that case, the determinant would be zero. That's not possible. That would not be a state transition matrix for any system. So let's say that we have some a, we got e to the power 80, and this is what we have. So small a minus t e to the power 80, 4t e to the power 80, 1 minus 2t e to the power 80. A is any scalar. So we have to reconstruct matrix A. So we already know if this is the state transition matrix, then it should satisfy the properties that we've just recalled, right? So let's check. If E at time 0, let's say this is phi of t, it's phi of 0 identity or not. So this is 1, 0, 0, and this is 1. So that's correct. This is a state transition matrix. And how do we relate the state transition matrix and the A matrix? That's by this differential equation, right? This is A by T. And since A is a matrix of the LTI system, we can actually compute this at any time, let's say 0, and we can get the A matrix back. So let's see. Mm, think substitute this. So d by dt of this whole matrix times A times 5 from the previous one. Both sides computed at t equals 0. So the A matrix would be dependent on the scalar A, right? So A is A plus 2, minus 1, 4, and A minus 2. Right. So again, there's another question. You can try this out later. This is again a state transition matrix e to the power 80. You have to figure out what A is. So again, using the same identity, you can figure out what A is. Also, if you have to verify if you have done all these computations correctly, after you have A, you can maybe just compute e to the power 80 back and see if they match. All right, that's it for today. If you have any questions, you can ask me now. Yeah, that's right. Yeah, all right. All right. Yeah, that's all right. Thank you.